Today we are going to do a follow-up on the video on oscilloscope basics. I wasn't planning to do this video, but I got some comments that I thought were worth responding to. And if you'd like to make comments about any of my videos, please do so and I will try to respond to them. And our first comment comes from Airwood99, who says, some students think that the coupling switch, DC/ground/AC, that's this switch right here, when set to ground shorts out the unit under test. But no, it's safe as the input is isolated at that setting. That's a good point. It never occurred to me that switching the input coupling to ground would short out my circuit, because that doesn't make any sense. If I could short out my circuit by simply setting this to ground, then if there's any significant voltage in the circuit, I could have sparks and smoke and all sorts of undesirable things happen. And so it wouldn't make any sense for me to design an oscilloscope so that could happen. But from a new person's point of view, they might think, oh my gosh, I need to be careful not to short my circuit to ground here. Well, let's take a look at the way this switch is wired into the oscilloscope, and we see that when we are in the DC position, we simply have a direct connection from our probe into the amplifier. When we set it to ground, we are shorting the input of our amplifier to ground, but we are disconnected from our circuit. So we are safe. All this does now is give us a zero voltage reference so we can adjust our vertical position and put our zero voltage wherever we happen to want that on the screen. When we switch it to AC, we are essentially putting a capacitor in series with the probe, and remember the mantra about capacitors, capacitors block DC. So sometimes I might have a signal that has a mixture of both AC and DC, and if I only want to see the AC component, I can switch this to AC. That will block the DC part of it, and then all I can see is the AC. Let me give a demonstration of what I mean. Normally, I leave this in the DC position, because then I see exactly, for every point of time, exactly what voltage I have coming out of my circuit. Right now I have my function generator hooked up to here. It's set up to 1 kilohertz at 10 volts peak to peak. So I'm going up to +5, down to -5, up to +5, down to -5, 1,000 times per second. So let's add some DC to this AC and see what happens. I'm going to add 2.5 volts of DC, and look what's happening to my sine wave. So I added 2.5 volts and the entire wave simply moved upwards. Remember, moving upward is higher in voltage, moving downward is lower in voltage. So every point along this wave had 2.5 volts added to it. Let's take it back down to where it was. So now I'm centered on 0 volts. Set this to ground. See, there's our 0 volts. Put it back to DC coupling. There's our sine wave going up to 5 volts, down to -5 volts. Let's add that 2.5 volts back to it. And every point in that wave was moved up by 2.5 volts. So now, instead of going to +5, -5, I'm going up to +7.5 and down to -2.5. And the entire wave is now centered on 2.5 volts. Let's make that 5 volts DC. So now everything has been pushed up by 5 volts. The wave is now centered on 5 volts. It's going up to 10 volts, down to 0 volts. Every point has had 5 volts added to it. Let's take that up to 7.5 volts. Now we are centered on 7.5 volts. We're going up to 12.5 volts, down to 2.5 volts. So everything has simply had 7.5 volts added to it. So now I have a combination of 10 volts peak to peak sine wave plus 7.5 volts DC. So my wave is still 10 volts peak to peak. I'm going up to 12.5 volts, down to 2.5 volts, a 10 volt difference, but I've also added 7.5 volts of DC, so it's now centered on 7.5 volts. So the DC coupling is showing me exactly that. If I move this to AC coupling, it's going to remove that DC component. And watch what happens. So it simply removed the DC, and now I'm centered on 0 volts again. So let's say I'm only interested in the AC component, and I want to measure how much AC I have, which is 10 volts peak to peak. I can see it centered on my 0 volts. Hit the ground, there's my 0 volts. Go back to AC coupling, there's only my AC component. Goes to +5, down to -5, showing my 10 volts peak to peak, and there's my AC component. But if I want to see everything, I move this over to DC coupling, and now I see everything that's there. So now you see I actually have a wave that's going up to plus 12.5, down to plus 2.5, plus 12.5, 2.5. So my 10 volts peak to peak is riding on top of 7.5 volts DC. Go back to AC coupling and you don't see the 7.5 volts DC anymore. So normally I will keep this set to DC so that I can see my entire wave and know exactly what I have. But let's say I have some AC riding on top of DC. I can move this to AC and only see the AC part and measure that AC a little easier. Set it to ground, get my 0 point, set it to AC coupling and measure my AC. And then if I want to see everything again, I can move this back to DC and see my actual true input. Another use for the AC coupling is if I have so much DC in my signal that some or all of it is pushed off the screen. Let's see that happen if I switch this to 2 volts per division. So now I have 7.5 volts DC, that's 2, 4, 6, 7, and right about pretty close to the top here. So most of my signal is pushed off the screen. Well, if I want to see all of my AC component, I've switched this to AC coupling. That removed my DC component, and now I can see just the AC component. And if you change your range, you should double check your ground. There we go. Back to AC coupling, and we can see I'm going up to positive 5 volts, negative 5, positive 5, negative 5, centered on my 0 volts. But if I go back to DC coupling, it takes it back off the screen where I can only see part of the AC component. But if I move this back to 1 volt per division, I can see the entire wave. So remember that DC does not mean it's for measuring DC voltages and AC is for AC voltages. DC coupling simply means I'm directly coupled to the amplifier. AC coupling means that I'm coupled through a capacitor and I block any DC component. And I normally keep this at DC so that I can see my true wave and see what components are there. So here I can see that my sine wave actually is riding on top of some DC, and I can estimate how much that is, 7.5 volts. So I have 10 volts peak to peak riding on top of 7.5 volts DC, and I can see all of that. But if I want to remove that DC component, I flip this to AC coupling and then only see the AC part of the component. So that's how the input coupling works. And our next comment comes from this user. Thank you. Waiting for part 2 to talk about triggering, etc. Well, I wasn't really planning to go much beyond what I did on the analog scope, but since you brought it up, I'll talk about the triggering. That is this section up here, and there's a lot of controls there, but it's not really that complicated. It's more fiddly than it is complicated to know what it is. Sometimes I have to really fiddle around with the triggering to get this to work the way we want to. Right now I'm having no trouble at all because of the way I have it set up. But let's talk about what the triggering does. The oscilloscope is sweeping a beam of electrons across the screen to make the trace that we see, and the triggering tells it when to start that sweep. Let's look at the source switch. This tells the oscilloscope what to watch to decide when to trigger the sweep to go across. Right now it's simply set on channel 1. Here's my input on channel 1, so it's looking at this for the source of what to start the sweep from. Let's set this to channel 2 and see what happens. Let me crank up the brightness just a little bit here. Well, I don't have anything going into channel 2, so it simply sweeps whenever the beam is ready to go, and it's kind of making an interference pattern with the wave and the time it's ready to go, so we're getting this interesting little pattern here, but it's just going and then going again, and it's just a little bit offset one from the other, and we get this interesting pretty little pattern here, but maybe not too useful for anything. The next position is alternate, so it triggers on channel 1, then it triggers on channel 2, then channel 1, then channel 2. And so we get something to trigger off of, and we see the beam going across when it is ready on channel 1. And finally we have external triggering. Since I don't have anything going into the external trigger input, once again it looks like it did when I had it triggering on channel 2, it just goes whenever it's ready. So we would use that external triggering if we want to trigger off of something that's not in the signals we have that we are testing. So let's set it back to channel 1 so we can see what we're doing. The next switch down here is just the input coupling for the trigger amplifier, and it has the AC and DC coupling just like the main amplifier does, and it solves the same problems. If we have so much DC that it's not finding something to trigger on, we can set it to AC, so it doesn't really matter right now whether it's on DC or AC. This particular scope also has a low frequency and a high frequency. The low frequency is for frequencies below 10 kilohertz, the high frequency is for frequencies above 10 kilohertz. Not all oscilloscopes have that feature. The next thing to look at is my trigger level, and that tells the oscilloscope at what voltage to begin sweeping the beam across the screen. Right now I have it set to start at 0 volts when it's on its way from negative to positive. So it goes down to minus 5 volts, and as it crosses 0, it starts the sweep and goes across the screen. And that's normally where you'd want to have it, because if we're trying to measure frequency, it's easier to measure where we have the angled slope there when we cross 0. So we set it to start sweeping at 0 volts, follow the wave through one complete cycle. When it crosses 0 volts again, that's one cycle. Here the time base is set at 0.5 milliseconds per division, so 2 divisions is 1 millisecond. Takes 1 millisecond to complete one cycle. That means it's 1 kilohertz. Now if I want that to begin at some other voltage, I can turn this clockwise or counterclockwise. I can turn it counterclockwise and notice that it looks like my wave is moving right and left. But what's really happening, if you look carefully at the left side of the screen, you'll see that it's simply starting at a different voltage. The way I have it set right now, I can go all the way down to about, looks like about 2.5 volts. So it's triggering at minus 2.5 volts on its way up, and I can adjust it to 0 and all the way up to looks like about 3 volts. And so I can adjust the voltage where it begins for whatever convenience I need to do that for. But normally you would keep that at about 0 volts. Let's take a look at the mode switch here. Right now it's in the out position, which is for auto triggering. And that is constraining my trigger voltage to be within the wave that I have on the screen. So the oscilloscope is looking and seeing, oh, you're going up to about plus 5 volts, about minus 5 volts. I'll keep your trigger level somewhere within there. So I can't mess it up. I can't get it to trigger outside of the parameters I have. But if I set this to normal, now let me turn this clockwise and notice my trigger voltage is going higher and higher and higher, to about 4 volts, 4.5 volts. And when I exceeded 5 volts, the highest point of my wave, notice it's kind of jittery there. Let's crank it up a little bit more. It's not sweeping anymore. So I have it set to sweep at maybe, okay, start at 6 volts. Well, it's never reaching 6 volts, so it never starts the sweep. If I crank this back down slowly but surely, there we go. Now my trigger level is back down to 5 volts, and it has something to trigger on, and I can adjust it down further. There's 0 volts, about minus 2.5 volts, and looks like I can only get down to about minus 3 volts and it cuts out. Just this particular scope. Other scopes might not behave exactly the same. So I can get my trigger level outside my signal that I have on the screen when I have it in normal mode. But if I put it back in auto mode, it becomes fairly foolproof, and at least I'll have a sweep on the screen. So if your screen is blank, you might want to check and make sure you're in the auto mode rather than the normal mode, so that it constrains what voltages it will trigger at. Finally, we want to look at the slope, which tells us to trigger either on the positive going or the negative going side of the wave. So right now it's triggering on the positive going. It goes down to minus 5 volts, triggers at 0 volts. If I press the slope, now notice that it's triggering when it's going from positive to negative. So now I have it triggering at 0 volts when it peaks at 5 volts, is dropping down, crosses 0 volts and triggers. And then I hit the button again, and it looks like I'm flipping the wave over, but notice at the left edge of the screen, it's simply changing whether it triggers on the positive going, as it does here. You usually have to adjust it every time you press the switch. So there it is, triggering on 0 volts, going positive. Hit the slope button. Now I have it triggering on 0 volts, going negative. There are some other features on this scope that I don't want to talk about in this video, but I'll give them an honorable mention. Here's the vertical mode. This is a dual trace scope, so I have 2 inputs, a channel 1 and a channel 2. And so I can actually have 2 traces go across the screen, and this controls how those are displayed. Either look at channel 1, look at channel 2, look at both. And if I have a slow sweep going across, what I would have is see one channel, then the other channel. One channel, then the other channel. So I can tell it to chop between the 2, and I can see both traces at once. Or at higher speeds, I can have it alternate between the 2, and it looks a little better on the screen. There's also a component testing feature on here that I have to give a try. I can put transistors and diodes on here and get a characteristic trace. I'll have to try that sometime. I also have a delayed sweep on this scope where it can be triggered and then wait a certain number of microseconds or milliseconds before the sweep actually starts going across the screen. And that can be handy if you need to see an event that actually ends up missing the screen because it happens too late. So you can actually tell it to delay the sweep a little bit. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.